Hi dear students, I'm Dr. Mohammad Ahmad and welcome to School of Chemistry. This is our second tutorial of the series concentration, and in our first tutorial we have discussed molarity and some basic concepts of concentration, formula to calculate molarity, and some related practical problems. In this very tutorial we are going to discuss another important and commonly used concept of concentration term, parts per million. uh, I would advise you to keep your pen, paper and calculator with you. You may need to take notes. As far as parts per million is concerned, it's commonly used in two ways: weight by weight and weight by volume. uh, So weight by weight parts per million, as you can see here, the formula is given. It's mass of solute divided by mass of solution into 10 raised to power 6 or 1 million. And important point here is that the mass of solute as well as mass of solution both should have same mass units. That is, if solute is taken in gram, then mass of solution should also be taken in gram. And if it is taken in milligrams, then the mass of solution should also be taken in milligrams. This is important here. And to practice this very simple formula here, we have a numerical problem here. Calculate the parts per million of weight by weight if you have 20 microgram of zinc which is present in 200 gram of an alloy sample. Amount of zinc is given in micrograms, 20 microgram, and 200 gram of the alloy is the mass of your solution. Actually it's a solid solution. And in order to calculate, we will use this very formula here. So we have mass of zinc, which is 20 into 10 raised to power minus 6 gram, because 1 microgram equals 10 raised to power minus 6, and divided by mass of solution, which is 200 gram, and then multiplied with 10 raised to power 6. So here you can see that this 10 raised to power 6 is going to be cancelled with 10 raised to power 6, and grams are going to be cancelled with grams, and we are getting this value here, 0.1 ppm or parts per million. Keep in mind that parts per million concentration term is normally used when we have lower concentrations of solute or we have dilute solutions, and these ppm values have no units. They are only the numbers. They are parts per million, parts of solute by weight to million parts of solution. If we go ahead, the second most commonly used ppm value is weight by volume. So weight by volume means that your solute will be taken in mass, in grams or in milligrams or in micrograms, and your volume of solution will be considered here in respective units. So the formula here to be noted is that ppm weight by volume is equal to mass of solute in grams, then it is divided by volume of solution in ml and multiplied by 1 million. So rather than using mass here in weight by volume, we will use volume here, and the point to be noted is the units again. If you are taking grams here, mass of solute, you will take ml here, and then this formula will work fine. It will give you exact value of parts per million. Similarly, if the mass is in milligram, not in gram, in milligram, then you will use volume in microliter instead of ml. So here the volume will be in microliter when the mass is in milligram here, and multiplied by 1 million, and will give you parts per million weight by volume. And normally the expressions which are used to denote part per million in terms of concentrations, it could be like milligram of solute per liter of solution is parts per million. We can say if there is 1 milligram of solute per liter of solution, then it will be referred to as 1 ppm. And if there is microgram per ml, that is also ppm. So we have basically decreased the concentration term by 1000 times, milligram to microgram, and similarly we have changed liters to milliliters here. So say you have 1000 microgram per ml, then it will be 1000 ppm weight by volume. Another could be nanograms per microliter, will also be referred to as parts per million. If you have 10 nanograms per microliter, the concentration will be 10 parts per million weight by volume. Another interesting thing to understand is that if you have a solution of 1 gram of solute per liter of solution, it can also be written as 1000 milligram per liter. 1000 milligram of solute, of course, because 1 gram equals 1000 milligram. And 1000 milligram per liter, just from this notation here, is 1000 part per million. This is normally the solution which are usually make to have a stock solution, and that stock solution is used to make further working solutions like 100 ppm or 50 ppm or something like this. So this is a kind of standard value, that 1 gram of any solute dissolved in 1 liter will give you 1000 ppm of that very solute. In order to understand the concept of ppm concentrations, both weight by weight and weight by volume, this slide will help us out in having a very clear concept. In our last tutorial, we have seen the conversions of mass as well as conversions of volume. Now we will relate these conversions to express ppm values. As we know that ppm weight by weight is mass of solute over mass of solution with same units of mass into 1 million, or we can also see that 1 ppm is equal to 1 milligram of solute per kilogram of solution. So how it can be explained actually is that milligram of solute per kilogram of solution. If you see here, milligram to kilogram, there are 2 conversion factors, each of 1000. So 1000 into 1000, 10 raised to power 6, or 1 million. So we can say that 1 milligram is 1 millionth part of a kilogram. Similarly, 1 microgram is 1 millionth part of a gram, and hence 1 nanogram is 1 millionth part of a milligram. Say for example, if we have 100 microgram of solute in 1 gram of solution, then that will be referred to as 100 ppm weight by weight. So this is how these concentrations are related to each other. Similarly, if you speak of ppm weight by volume, it means that your solute is in mass and the whole solution is in volume terms, or mass of solute in grams divided by volume of solution in ml multiplied by 1 million. So these are two terms actually now related, mass and volume, gram ml into 10 raised to power 6. In order to understand the concept here, see, water, if we take density of water as 1, we can say 1 liter of water measures approximately 1 kilogram, or 1 milliliter of water measures approximately 1 gram. So 1 ml measures 1 gram. As part per million is a millionth part, so these arrows will show you that how parts per million weight by volume are basically related. If you see here, milligram of solute per liter of solution. So milligram is millionth part of a kilogram, and kilogram is equivalent to 1 liter, because 1 liter of water measures approximately 1 kilogram. So milligram per kilogram is ppm weight by weight, and milligram per liter is ppm weight by volume. In the same way, microgram is millionth part of a gram, and gram is equivalent to ml, because 1 ml of water equals 1 gram if we consider density of water is roughly 1. So microgram per ml is also part per million weight by volume. Say you have 10 microgram of a specific solute dissolved per ml of solution, then it will be 10 parts per million weight by volume. Likewise, nanogram per microliter is also part per million weight by volume. Say 100 nanogram of a particular solute dissolved per microliter, then we can say that is 100 part per million. So this is the whole concept actually. This slide is very helpful in understanding the concept of ppm, both weight by weight and weight by volume. You can play around with numbers to make this concept more easy for you, and you can get your expertise here. There are certain other small areas which we basically need to understand. See, 1 gram of solute per 1 kilogram of solution. Weight. So if we compute or calculate part per million weight by weight, then 1 gram divided by 1000 gram multiplied by 10 raised to power 6 is 1000 ppm. It means that 1 gram of any substance per kilogram of solution equals 1000 ppm, as we have calculated here. So this is a standard value actually, which is normally used extensively to make solutions. 1 gram of substance per kilogram of solution equals 1000 ppm weight by weight. As 1 gram equals 1000 milligrams and 1000 milligrams per kilogram equals 1000 ppm, so we can say that 1 milligram per kilogram equals 1 part per million. It's the same concept as we have seen in the last slide. Or 200 milligram per kilogram is 200 ppm, weight by weight. In order to understand the concept at relatively more complex level, there is a problem here, and it states that if you have 2 grams of sodium chloride in 1 kilogram of a rock, then you need to calculate ppm weight by weight of NaCl first, sodium ions second, and chloride ions third. So you have 3 portions of this numerical A, B, and C. First one is simple, as we have seen here, that we have 2 grams is the mass, which is 2000 milligram. So 2000 milligram per kilogram equals 2000 ppm, just like this. 200 milligram equals 200 ppm, 2000 milligram per kilogram equals 2000 ppm. Other way around, we can also calculate by using the formula. ppm weight by weight equals mass of solute in grams divided by mass of solution into 1 million equals 2000 ppm. This is how we can calculate ppm values of any given solution if both solute and solution are given in mass. In order to calculate the ppm values of sodium and chloride ions, we need to go further down to incorporate certain factors here. And determination of these individual ions, we need to follow these steps. First and foremost is that the molar mass of that very compound. For example, in this very particular case, we have sodium chloride. The formula mass of sodium chloride, which is 58.5, will be divided by the ionic mass of sodium ion, which is 23. This will give us a number like here 2.54, and this basically tells us that 2.54 grams of sodium chloride will contain 1 gram of sodium ions. And by using this factor, we can calculate parts per million values of sodium ions and chloride ions as well. So the first step is divide molar mass of the compound by ionic mass, to basically get this factor. This number will be utilized to calculate the quantity of sodium there in the given quantity of the salt. So the second step would be 2.54 will be utilized here like this. Use this factor to calculate amount of the ion in the given mass. Given mass in our numerical problem is 2 gram. So if 2.54 grams of sodium chloride contains 1 gram of sodium, then how much will be there in 2 grams of sodium chloride? So 2 grams of sodium chloride will contain sodium ions. 2 divided by 2.54 equals 0.787 grams. So here what we can conclude is that 2 grams of sodium chloride have 0.787 grams of sodium ions. In order to calculate ppm of sodium ions equals 0.787 gram, which we have calculated here, divided by 1000 gram, that is the mass of solution, multiplied by 10 raised to power 6 is 787 ppm. Likewise, if we need to calculate ppm concentration of chloride ions, then we need to divide molar mass of sodium chloride by the ionic mass of chloride ion, which should be 35.5 here, and we get 1.67. And this 1.67 means that 1.67 grams of sodium chloride contains 1 gram of chloride ions, or this is the factor here. So whatever the quantity you have, divide this quantity with this factor and we get the mass of chloride ions which is present there in that very sample, in 2 grams actually. So we have 1.197 gram of chloride ions. We can divide this by mass of solution and multiply with 1 million to get parts per million values. So the calculation of this factor is important in order to calculate part per million concentration of certain ions when they are present in their ionic compounds, or certain atoms when they are part of a compound. There's another solved example that how we are going to prepare 1000 ppm solution, weight by volume, of potassium ions in 2 liters if you are provided with potassium chloride. So here we need to understand that we have potassium chloride. Total volume of solution is 2 liters. Concentration we need is 1000 ppm, weight by volume. So the formula here is weight by volume ppm equals mass of solute in grams over volume of solution in ml into 10 raised to power 6. So ppm is 1000, mass we need to calculate, volume of solution is 2000 ml because it is 2 liter and 2 liters are equal to 2000 ml, and according to formula if we put gram here we need ml here. So mass is equal to 2 grams. We need 2 gram of potassium ions, but in actual we have potassium chloride, not potassium ions with us. So we'll have to calculate that how much potassium chloride will be required to have 2 grams of potassium. So step 1 is molar mass of potassium chloride, which is 74.5, divided by ionic mass of potassium, which is 39. We get this number 1.91, which tells us that 1.91 gram of potassium chloride contains 1 gram of potassium. How much we need? We need 2 grams. So it means that 1.91 multiplied by 2 is 3.82 grams of potassium chloride there. So we have to dissolve 3.82 grams of potassium chloride in 2 liters to get the required concentration of 1000 ppm of potassium. And keep in mind, this solution will not be 1000 ppm of chloride or 1000 ppm of potassium chloride. It will only be 1000 ppm of potassium ions. In order to calculate concentration in terms of chloride or in terms of KCl, we have to perform calculations. Here are some practice problems for you, and these are 4 problems you can do at your home, keeping those formulas in contact and practicing these. For example, here first question is that how many grams, so you need to calculate grams of ammonium sulfate are required to prepare 1500 ppm weight by volume solution in 500 ml. So volume is 500 ml. Mass in grams need to be calculated. ppm values are given here, and you will use the formula that mass of solute divided by volume of solution in ml multiplied by 10 raised to power 6 equals ppm, and ppm are given, and there's no need to put molar mass of the substance here. Similarly, calculate concentration of a glucose solution which is 0.3% weight by volume. 0.3% weight by volume means that 0.3 gram of glucose is dissolved in 100 ml. So we have volume of solution, we have mass of solute, and we can easily calculate P2 gram. So it is there, and 500 gram of an ore, so this is your weight of solution in grams, and we need to calculate ppm, so it's not very difficult. Question number 4 is how will you prepare 2500 ppm solution of potassium sulfate in 1 liter. So volume of solution is 1 liter and ppm values of 2500. First step would be that you will need to calculate how many grams of potassium sulfate are required. There's no use of molar mass actually, so you will calculate the amount in grams of potassium sulfate which is required to prepare this solution. And second step will be that how will you prepare this. You will take that quantity of salt in 1 liter flask. You will add some water, dissolve that salt, and then you will add more water up till the total volume of the solution becomes 1 liter. So this is how it will be made. So this is it for now. In our next tutorial we will basically study the interconversion of molarity and parts per million, that how these two concentration terms can be interconverted, that if you have given molarity, how will you convert it into ppm concentrations. Thank you.